Welcome back. Today we are going to learn the most important topics in the Introduction to Statistics and Probability class that everyone, I believe everyone on earth who studies this kind of course, we have to encounter eventually, which is a normal distribution. And oh, by the way, we are going to use this normal distribution until the end of the lecture, so like 7 weeks, 7 lectures from now on. So make sure you understand what this is and what is going on there. Right, so far we have compute discrete distribution, where we can have some graph and see the shape like using some math formula. Then we can then we move on to the continuous part, when you measure something and then you get some kind of like curve. Instead of the height, we represent probability of some number that falls in between two values as an interval. And we know that, okay, we have to find the area somehow. If it's simple shape, we can find. If it's not, then we have to use some maybe crazy formula. Right, but now we are going to this normal distribution is one of the continuous probability distribution function. In the sense that it's a graph. Right, we are going to get, it's going to be some kind of curve. Right, and then eventually we're still gonna consider the area under the curve between 2 points, and again find the probability of the value falling in between 2 endpoints. But the question is, why does the curve that we are seeing here is more important or more common than other types of curve of continuous distribution function? So let's imagine that we do stuff. Maybe have some kind of measurements, but for example, we can measure height of people and try to make some nice graph. And by the way, since we cannot measure the exact height, right, but we can somehow make a histogram instead, which makes more sense. Histogram means instead of having one single bar represents one single point of data, right, we make one single bar represents a range of data. So for example, you can measure height, and let's make it maybe 140 to 141. Okay, so we count how many people have heights between 140 and 141 and put them all into a single bin, the same category. And now the height will measure the number of people who fall into that category. Let's say there are 5 people. And then repeat that for all the heights. Well, actually, let me start from, let me make a Y range of 10, 140, 145. And next one with, of course, 150 to 159. Maybe there are more, like 12. And then next bar would be 160 to 161. Maybe that's 21. And then we have just repeat that until we run out of people. Also, it's not 161, 169. And next we can have 170 to why is that green? 179. And then some people, of course, those tall people with some high height. Maybe it's 180 to 189. Maybe there are 3 or 4. For example, that would be a pretty cool way to take the data we have and turn it into a nice graph, a nice histogram. But you can see it's kind of a trend here. Right, first of all, it seems like the middle seems to be the most popular one, or the most common one. And that's kind of intuitive, because if height are actually random, like there are several factors that contribute to how high a person be, like genes, nutrition, luck, maybe, I don't know, some other random factors, and all those factors combine together to make people higher or taller. And if there are enough factors, then most people will be around the average or around the middle. And some people will be really tall. That happens, but there shouldn't be that many compared to the middle. And also some people are maybe pretty short, but again, not that many people should be too short. So this is one way if you collect some data and present that as a histogram. But you can see that like only 5. And so maybe you say, oh, 5 is not accurate enough. So why don't we just let's say 1, yeah, let's go slowly, maybe 5. 140 to 144. Yeah, that's gonna be a smaller one. The next one would be, oh, maybe I should, maybe it's this, 140 to 144. There, and then 145 to 149. And then some people will fall in between 150 and 155. Right, and so on and so forth. If you split each bar into 2, we're gonna get more bars. In this case, it's gonna go from 5 to 10 bars. Right, but still, even if we split that in that many, even though they fall smaller, the shape of this graph should still look the same. And more people should still be centered around the middle point of this 5 data, and there should be fewer people that are in the extreme ends of both sides of this bar. Right, but then of course we can continue, right? By just stop at 5, and you can, for example, if you have enough information, if you have a data set of people of 1 million people, for example, of course it will be maybe more accurate for analysis to split that into maybe a size of 1. So for example, the first one could be 140 to 149.9. Oh, sorry, I think I said 1. It should be 140.9. And next bar will be 140 to 140. Oh, sorry, 141 to 141.9. Right, and so on and so forth. So we can still make a histogram, a nice histogram that we can analyze and visualize, right? And if you have enough information, and if you keep repeating this over and over, you will notice something. You will notice that if eventually, like the curve would look, that's my head. The curve would look like that. Suppose this is pretty small. Let's say each bar has contains all the height of with an interval of size 0.1. Maybe the first is 140 to 140.09, for example. You can squeeze, you can divide or sub. You can divide each range as small as you want. But then eventually, the discrete information and this discrete set or this histogram, you're gonna look something like this one, which I am pretty sure you have seen this before on internet somewhere. Right? And so that's the reason why we are going to use this curve. Because this curve is what we will get eventually if we have a large enough data set, and if we split each one into a small range. And the nice thing about it is it's not limited to just human size. Whatever that nature produce, it's so extreme that it's gonna give you something totally different, right? All of those curves, all of those histograms, with the small bit, gonna give you the same or at least similar kind of shape. Maybe if you wait some x, maybe it's gonna be like that, but still, yeah, so it's still going to have some peak there and then down, and then maybe your grade of this class or of overall starting from your birth, it's gonna look at some kind of nice curve. Like, oh, and if you think about grade, like maybe some people you have pretty low grade somewhere here, still is this curve. Maybe you have high grade, you are intelligent being, and it's even though like you can see that the position, the distributions of your grades are different. Maybe the height will be different, the density are different. Then these shapes should still be similar to each other. And so that's why we didn't just invent this curve because it looks nice. We use this curve because it is natural. This is the production of nature's doing. So the next question is we have to ask, how can we produce such a curve? We can collect some data, of course, and plot some nice curves, right? But can we get some exact information, exact point, exact function? And before we go to the function, let's see if we can produce it in somewhere that somehow that is reproducible. So we have this one which called the Galton Board. It's a famous board. And if you have a link, you can click on that. If not, I will put it in Google. Oh, sorry, in YouTube, on YouTube. Right, so for now, let's I think I have to turn it on. So turn the music off first. Right, and then go to that clip. Okay, it should be on the right. ASMR. Now it's slow motion. Math. Right, looks nice. You can watch more clips, of course, if you search this keyword of the Galton Board. Right? What's going on here? Let me explain. I believe you have seen this kind of, let's say, the slot machine, or is it slot machine? Yeah. Anyway, it's kind of like gambling machine. You know, the way you play is the machine's gonna drop a single ball from the top, and once that ball hits the pole, or the whatever it is, the pole there, right, it will either bounce to the left or right, right, depending on the slide position where it drops. If it's slightly to the left, then it tends to bounce to the left, right, and that repeats. Let's say this ball bounce to the left, right, then once it hits the next pole, then it's gonna kind of have to decide whether it wants to continue to the left or go back to the right. And then there are many factors that control how the ball behaves, like gravities, the materials of the balls, the size of the pole, whatever. But of course, we cannot control all the oops, my bad. All the factors. What we can see is, like, you know, we produce this board, this machine, and then drop lots of balls, as you can see in the image, and see what the result could be. And so you have this ball, and then the machine is let's say there are only this many. There are 5 pegs at the end, so there can be 6 different positions. And so the first ball drops, and then, you know, bounce, and then goes there. And there's no way to know. That's just a single ball. It's just like when you sample. If you go on the street and like pick the first person you see, and ask how high she or he or that person is, like, you're gonna get one single point of data, which doesn't say much. And that's why we have to sample. Like, so we have to get lots of information to see the trend. So if we drop hundreds of balls, they are gonna, you know, bounce back and forth, and eventually, like, they are gonna be accumulated in the bottom, in this bar at the end. And you can see that the shape will look like what we just, you know, we just draw, that is the shape for the normal distribution. And the nice thing is, it doesn't matter, like, it doesn't matter the number of balls or how many times you try to run this experiment. If you you can see from the clip that, okay, the first time it has some slight maybe error, and that's the lie on the machine, but maybe for some reason there are more balls in the maybe second column, for example. But they still look, they still pretty close to the curve that they predict. And then if you repeat that, like, reset the whole board and let the balls fall back to the top, to the top, and then you flip it again and repeat the experiment. And no matter how many times you do it, the balls will always be pretty close to the curve, and the predicted curve. And then this is where we have two separate areas. The balls represents the samples. Like that. Oh, if you do it once, then you get this set of samples. If you reset the whole thing and repeat, you're gonna get a different set of samples. Yeah, but on the other hand, we also have this curve. In this nice curve, we will say that it's the theoretical curve or prediction in this case. Let's say, oh, no matter how many times you do, and most of the balls you follow this curve, and there will be fewer balls on both ends, and because they are too far, and there will be more balls in the middle, because it's easy to bounce in the middle. And so that is for silk on hand. We link the samples here, and then we use the curve to get the theoretical function or information that we can compute. And what is this curve? Like, oh, the curve is there. And take a look at 5 seconds, and you can remove that from your brains. It's the function. Again, is it a function of one single value x? There's an x there, and everything else are just whatever. Let me remind that. Okay, do not remember the formula. Like, this is just to let you know that okay, there is some function. Like whatever your calculator or website or whatever does, it is using this function to compute the numbers or the values. Okay. And once you know, oh, it's some kind of formula, then you don't have to worry with it. Because we want to say that okay, if we have a graph and use that formula or that function to plot the graph, the result would be this curve. And what we want to say is we want to look at this curve, right, where we have the mu, the average, and the center part of this curve, and then we have the sigma as the spread that says it's a curve wide or narrow. That's the curve. Yeah, it's a curve wide or narrow. And before we move on, you might want to ask like who invented this kind of curve? Like that doesn't have to be like this complicated. The answer is kind of yes and no. It doesn't have to be this complicated. But the factor here, right, that we multiply is to make sure that the total area is 1. Remember last time? Right, for the function to be continuous, the probability distribution function, the total area has to be 1, so we don't have to scale things up and down. Right, but so we can kind of ignore that part, and then let's take a look about this part. Right, it's still complicated, but there's some nice explanation there, which if you're interested, I suggest you go take a look at that. I should have this is another nice YouTube channel that I recommend you follow. This person is Eddie Wu. He's a great math teacher in Australia, I believe.
So far, all we've been doing is looking at the numbers of it, right? Like this percentage, that score, all the rest. But so far through this topic, we've actually been dealing with like calculus and stuff, right?
It's gonna involve some calculus. But the nice thing about the intuition, why it has to have this that function, I suggest you watch them all. But let me skip all the way to that. And the thing is, we want to kind of make some models. We want to make a curve like that model what we have on the upper left. Okay, but the question is what kind of function has that kind of curve? And then we have to know some math. But the thing is the exponential curve has a property that the left and the left part, as you can see from the blue graph, converges. It goes to 0 pretty fast. So that's going to be useful because we want the area to be mostly in the middle. And then it needs to go down close to 0. Right, so that's a candidate. Okay, but the right part doesn't go to 0. And the right part kind of go to infinity. So we must find a way to make sure that they go to both zero. They go to zero on both to the left and to the right. And that's he has some meme there. Right? And the one way to fix it is to use kind of like the minus and absolute value to make sure that the values that the values that were going to infinity now it converts to zero instead. And then that is a nice curve. And that's kind of close, but again we have to like move the center a little bit. Oh, I think he skipped all the way to that. And once we have that, then we have to move the center and adjust the spread or do stuff. And eventually we're gonna get that to that function. So that's a way to use a function that we know before and adjust it to that so that it fits the curve. It fits the distribution that we usually encounter in nature. Okay, so we say a normal distribution because this distribution can have different positions. We can move it to the left or right, and we can have it wide or narrow. So let's take a look at some examples of this curve here. Here you can see the four curves there. And we have let's go from top to bottom. We have the blue curve, and mu is 0, so the average is 0. And we will learn next week that the mu or the average represents the center or the point where the graph is at the highest, at the peak. And so the average is 0. And then we have the standard deviation. Sorry, the variance, the standard deviation square. And that's gonna say whether the curve is narrow or high. Remember that if this value, the higher the value is, the redder. Is it more spread? I'm not sure about English. But anyway, and we can see that point 2 is small. We can agree that point 2 is small. Right? So if the variance is small, then the curve should also be narrow. It should be close to each other. And there's not much variance. And so that means most values should be close together to each other. And that's what the blue curve is trying to tell us. What about the red curve? Okay, next let's look at the red curve. It still has the same mu, the same center. And so you can see that the peak of the red curve here is also in the middle of the graph. Right, but here the standard deviation is 1. That means it is more spread than the blue curve. Okay, so the curve goes to both left and right. And also you can see that the peak kind of drops. Okay, because if the curve, if you don't drop the peak, if you make this kind of curve, then we encounter a problem here, which is that the area under the red curve is now a lot higher than the blue curve. And remember that we have to make sure that the area is 1. We can increase the size, of course, but the size effect is that we have to scale the curve down to keep the total area to be 1. So for example, if you spread that like maybe that far, and then the area of the red curve happens to be 2 times as high as the blue curve, then we have to drop the peak halfway down. So the total area is now half. And this is kind of like what we did here. The ratio is not 1, but the red point kind of almost halfway. Yeah. So that's for the red curve. And next one is the yellow curve. You can see it's still the same average, the same peak is there. But now the spread is now the variance is 5. We can agree that 5 is high, so it spreads pretty far. And of course, as a side effect, the top has to drop down. And which you can see that the number of data that are between there and there, and even like there, they are still pretty close to each other. Okay, so it is not uncommon to get the value that is very high or very low. And lastly, for the green curve, mu is -2. So the center here is back to -2, and then the spread is 0.5. 0.5 is narrow. And so you can guess from the shape that it's wider than the blue one, but it's still narrower. Yeah, it's wider than the blue curve, but it's narrower than the red curve. So it's kind of like halfway there, and that's why the peak is in between these two peaks. So all these 4 curves are the normal distributions. But the question is, which one do we use? Right, there are so many, depending on the values of mu and sigma that we put into the formula. And we're gonna answer that in next class. We have so many curves, right? But they kind of look the same, aren't they? And if they look the same, then we should have some standard curve that, you know, we can, let's take a look at this standard curve, and then we can scale it up and down. In the same way that, okay, if you want to find, you can find the area of the circle. That's easy, right? But what about the end oval? Right, the oval is kind of wider. Okay, but you can kind of adjust the width. You can kind of scale down, right, to make the oval a circle instead. And once you get the circle, then you can find the area, circumference, and all the way, right? And then you can then we can adjust the numbers or the results from a circle back to the ovals. And that's one way to kind of think what is the standard. We are gonna study just one single standard normal distribution, and hopefully in which you can see that's the case. And for any kind of curve or in any distribution, we can always go back to the standard one and do some math, and then use that information to make the conclusion about the new curve, about the distribution that we are working on. Okay, and there are several properties there, and I have actually explained before. So the center or the peak of the graph is still x equals to mu. Next one is interesting. We assume, for the sake of simplicity, we assume that the mean, the median, and the mode are all the same. Remember from the second week of the class that we say, that they can be different. And if they are different, they're gonna give you different kind of plots. Maybe it's skewed to the left, maybe it's skewed to the right. It depends on which one is higher or smaller. But now, the nice thing is about it is that the normal distribution is the symmetric. Okay, so what the mean? Mean is, remember, the mean is the average. The median is the middle point, and then the mode, the most frequent or the highest point, are all the same. And that's simplify lots of computation. And lastly, I didn't finish this sentence there, but it seems that standard deviation is the spread. And I already explained that. So again, the higher sigma square is, then the spreader, the curve. So yeah, we are looking at the mu, this theta, sorry, the sigma, the average, and the standard deviation. Next week we're gonna see how these numbers kind of like work together to get the normal distribution. But before we leave, let's make some quick notes. So we have some meme. Not sure if that helps or if that kind of leads you astray from remembering this distribution. We have normal, and then we have paranormal. Yay! And lastly, we have the extra one. Like we talk about the calculus. Remember that if I give you this simple shape, you can compute the area by hand. Sure, if you a triangle, you can also compute the area by hand. Okay, but once you go to any kind of curve, this is the exponential distribution, or what we just see, the normal distribution. And we have to use the math to compute the area under the curve between 2 points. Because we can no longer use the previous knowledge. How do you compute? If you haven't seen, if you haven't studied calculus at all, you can just appreciate it. Oh, that's interesting. If you do, then that's gonna be helpful. And for the full version, this one is still the same definition we had before. For for the function to be continuous probability distribution, then it has to specify two requirements. First, the value or the point of the graph has to be between 0 and 1. Oh. I made a huge mistake. It has to be at least 0. It can be more than 1. And that's one. And then the other one is the total area is 1. This is the same as before. That we learned in class or in 2 or 3 clips ago. Right, but in calculus, the area now has an exact definition that you can compute. And the area is this definition. When you see this curve rotation, you read it as the area. And then to complete area, you have to use the calculus. In this case, you have to use the integration, and you have to also put this limits from minus infinity, which is the far left, and then to infinity, which is all the way to the right. We find all the area under this curve, this function, and that has to be 1. And once we have these two, and then we can define the probability of the random variable or the value x to be between two numbers between c and d, to be simply the area between the 2 points, right, from c to d. And so that is exactly what we have done so far. We have the point c, we have the point d. We identify the area. We still define that area to be that probability. But now we have an explicit formula that we can use. And even if we don't know calculus at all, you can still use this formula in calculator to compute that area, the area you want. And so that's one way. That's if you know the calculus, that's gonna be helpful to understand that. And also we can move on to, okay, once we have the probability distribution function, how do we compute the expected value and the variance? Like how we compute the center and the spread? And the answer is still calculus. Right? The formula for expected value, for the continuous or for the discrete part, we have this. We have this notation. We add the sum of the values of the value times the probability of that value happening. But since we have calculus, we can kind of transform that summation for the discrete part to integration for continuous part. And another thing is x and f of x are the same, and they look the same in both sides. And x is a value, and that is kind of like how likely to get that value. But in calculus we use f of x. And then we have d of x, which is the notation that we always use with the integration part. And lastly, for the variance, you can also use that, but it's a slightly different formula. It's harder to compute, but if you have calculator and if you plug in the right function, the right values, then eventually you can get the value from that machine you are using. So that's the end for the normal distribution. There's gonna be some quick or not too difficult homework from watching the clip. Alright, see you next week.